os representantes aqui da empresa. Então, como nós estávamos colocando, hoje é dedicado a dispositivos móveis, nós vamos ter uma programação semelhante à de ontem. Primeiro, nós vamos ter uma palestra do Willem Visser, que gentilmente aceitou o nosso convite de estar aqui. Daqui a pouco o Lucas vai fazer a apresentação dele. Após a palestra, nós temos o coffee break tradicional. Se por acaso atrasar o coffee break, a gente entra em uma ou duas apresentações, depois continua as outras. Mas a expectativa é que a torno de 3 e pouco, esse coffee break já esteja aí. Depois do coffee break, a gente vai ter então 5 apresentações de trabalhos das equipes que fizeram parte dessa segunda turma de dispositivos móveis. E nós vamos ter uma comissão aqui julgadora na frente dos trabalhos que vão ser apresentados. E a melhor equipe vai ser premiada com um tablet da Samsung, né? Só que a premiação ocorrerá após a palestra sobre o projeto de aplicativos, que é um outro projeto que nós temos com a Samsung. Tá? Então, na sequência, a gente vai passar a palavra para o professor Lucas, para ele possa apresentar o professor Visser, que é da África do Sul. Tá? Ele ficou bastante contente com a camisa aí da África do Sul que ele viu.
Obrigado. Bem, boa tarde a todos. Nós convidamos o professor Willem para deixar uma palestra sobre verificação de aplicação do Android. Nosso projeto de tecnologias móveis, basicamente, o sistema operacional que nós utilizamos é o Android. Tá? Então, o professor Willem, na verdade, ele tem um aluno de doutorado, né, que está trabalhando, desenvolvendo algoritmos para checar corretude em programas que são escritos, que rodam, que executam com Android. Tá? Então ele vai dar uma palestra mais ou menos por volta de 50 minutos sobre os resultados que ele tem nesse trabalho. E aí a gente abre no final para perguntas. Tá? Então eu vou chavear para inglês, tá? Que é a última nativa dele, então vai ser a apresentação. E aí vou introduzir brevemente aqui com a biografia do professor. So Willem, thank you very much for coming to Manaus. We're very happy to host you here. The Professor Willem Visser, he works in the computer science division at Stellenbosch University, South Africa. Before joining Stellenbosch in 2009, he spent 8 years working at NASA Ames Research Center, where he was one of the research leads for the JPF-android project. His research interests include model checking, testing, symbolic execution, and model counting. He has been co-chair of the Automated Software Engineering Conference in 2008, will be the ICSI International Conference of Engineering Program co-chair in 2016. He is also currently one of the steering committee for ICSI and SPIN, and on the executive committee of ACM Soft, and is a member of the third board of the Transactions on Software Engineering and Methodology. Thank you.
Thank you very much. Unfortunately, this is now going to be a change of language into English because my Portuguese is not quite as good. I'm actually non-existent. So this talk is going to be about how we extended Java Pathfinder, which is this model checking tool, which I'll try and explain to you how it works a little bit. How we extended it to analyze Android programs. And firstly, though, I have to say that I'm only kind of like peripheral to this project in the sense that I'm a supervisor of, maybe the battery eventually died, but Ayla Fatimata, which is my student, she's actually the person really driving this project, and I know something about the model checking, and I know a bit about Android, and I know a bit about the combination, and hopefully I can convey everything to you. Another supervisor is Brent Fatimata, which amazingly is the same last names, but in South Africa, it's an extremely common last name, and they have no relationship. Okay, so firstly, where is Stellenbosch? It's like down there, and more specifically, if you look at the Western Cape region, which is the region around Cape Town, it's about 50 kilometers away from Cape Town. So you remember back to the previous World Cup in 2010, where the Cape Town Stadium is, that's about, let's say, 50 minutes drive from where Stellenbosch is. But more importantly, Stellenbosch is in the wine region. So that's where all the, I wouldn't say all the good wines from South Africa come from, but most of them. be slightly biased. And I have to say I quite like the wines. Now just a little bit, this is just what the university looks like. It's got a mountainous around the university, so it's actually pretty nice. We don't really get snow because it's too far south, but sometimes at the top of the mountain there's a little bit of snow, and then it's like everybody takes the cameras out and takes pictures like that. It's not a common sight. Now just for myself, I started off in Stellenbosch doing a master's degree. I hear from Lucas here that a lot of you also do master's degrees here. Very common in South Africa to do a master's degree, not quite so common to do a PhD because the job market is too good. People don't want to waste their time doing a PhD. I didn't say that. I would love to have more PhD students, but that's the reality. So I left for Manchester to do my PhD. And it's no coincidence that that is Old Trafford, because that's one of the reasons why I went there, was because I was a big fan and I wanted to watch the games. And I probably saw about 40 games in the 3.5 years I was there. It was pretty good. And in '98 I went to Silicon Valley, which I guess you all know where that is, but it's that little strip of land south of San Francisco on the west coast of the US in California, and just down to San Jose, which nobody knows about, but it's actually 3 times the size of San Francisco. And that's a picture kind of the NASA center there. So in the US there are, I think, 13 NASA centers. Most of us, pretty much me included as well, up to the point I went there, really only knows about the Kennedy Space Center because that's where all the launches are. They know about Houston because Houston we have a problem, and then there is the Jet Propulsion Lab where all the rovers are kind of managed from. But then there's also about 5 or so what they call research centers. So these are NASA centers. They don't really run missions, but they do research. And the one in Silicon Valley was all about software development, and I worked there. And actually the stuff, most of the first part of the talk is going to be what we developed when we were there and beyond. Then in 2009 I went back to Stellenbosch, and there's a reason why this picture now has the vineyards on it, because it's actually the same place. But I was less interested in wine when I was there in the beginning, but now I'm more interested in wine. So it's, and of course we make our own wine, but who doesn't, right? Everybody makes their own wine. No, I'm just kidding, but in Stellenbosch everybody does make their own wine. Okay, so that was my little circle of life there. Ada, she is a PhD student, just so that you can see the person who actually does this work. She's a PhD student. This picture was taken when she was in an entity that we have at the university called the Media Lab, where a lot of our students reside. That's Ada. So if you have any questions, that's her email. And so, I'll forward it as well if you want. Okay, so overview of the presentation. We're going to start by telling you a little bit about Java Pathfinder, and then on to what we call JPF-android, which is the extension for Android. That is the main focus of this talk. Now, JPF-android is what we call an extension. So in Java Pathfinder, you have the core project, and then you have extensions. And this is one of the main extensions, and it's intended to verify Android applications outside of the normal Android environment. Right? So it does not involve, say, Monkey Runner and whatever emulator. This is a standalone thing. And the idea is to detect runtime errors that would occur during runtime, and mostly logical errors, but also concurrency errors, because concurrency errors are kind of hard to track by normal means. So a model checker is pretty good at that. Okay, so this slide, I have to admit, I picked up from the web. It's my slide, I created it, but the problem is I created it in 2002. And I knew I created a slide like this, but I went to search on Google until I found my own presentation that somebody stored somewhere on a disk. And this slide comes from there. So it's a bit old, but it conveys the message. I wanted this slide to just in one slide show you what Java Pathfinder is. So you have Java code there. There it goes. You have your Java code, you compile it, and you get bytecode. Okay, now if you executed this bytecode on a regular Java virtual machine, you would potentially see one of the behaviors of the program, like this little red one down there. However, if you feed it to Java Pathfinder, which is a special virtual machine, Java virtual machine, facility to do search with, which I refer to as a model checker, then you can potentially see all the behaviors of the program. That's the fundamental thing that JPF allows you to do. So special virtual machine with a search component attached to it. So in terms of the kind of slightly more in terms of the structure of JPF, we take class files as input, as you saw in the previous slide, and also configuration. So the configuration will tell Java Pathfinder which class file to run, in which class file is the main, essentially, so you can run your Java code, and also whatever other configuration you want. So for example, if you want a breadth first search of the state space of your program, or depth first search, and so forth. And in the system itself, like I said, there's a core system and there's a bunch of extensions. The core system itself allows you to just model check Java programs, but sometimes you want to do fancy things. Like for example, in this presentation we're going to talk about Android. And Android, although when you look at Android code it looks like Java code, of course it doesn't run on a regular virtual machine, so it runs in a special environment. And in order to handle that special environment, we create a special extension of Java Pathfinder. And the output here is essentially some kind of report. Like for example, if you find an error in the code, it'll show you exactly how to get to the error and such like things. The vanilla version of Java Pathfinder checks for any uncaught exception. So if you have an exception thrown in your program and you do not catch it, then that would get reported as an error. Also, deadlocks and data races will be reported as errors. There are all kinds of fancy extensions of Java Pathfinder, like symbolic execution. I'm not going to talk about this here, but if you really want to know what symbolic execution is like, this is probably one of the best Java-based symbolic execution tools around. Now the history of the tool, it's been around for a while, so as you can see here, 16 odd years. Every time I use this slide, I have to update that number, but it's been a while been around for a while. The first version was actually created in 1997, but that was a different version than what you see here. That's what the red line indicates. That version was almost like the proof of concept tool that we built. Well, I didn't build, Klaus Abelard built. And it worked great. However, it had all kinds of shortcomings. And in order to circumvent these shortcomings, we created a new version roughly, well not roughly, exactly in 99. And that's pretty much where the clock starts for the 16 years. And the important features along the timeline is in 2003 we created this notion of an extension, which really was very important because up to that point, everything anybody did in Java Pathfinder was in the main part of the code, and which is of course, as we now know from software engineering, not modular and therefore not good. And so the extension interface was very important. Also in 2003 we managed to cut through the bureaucratic red tape at NASA to open source the code. However, it took us until 2005 to convince them that we can actually put the source code on some open source repository. Up to that point, you had to ask for the code. So in 2003, you could get JPF, but good luck essentially using it. From 2005, the actual complete development environment for JPF went on SourceForge. And it was the first NASA project ever for which this was the case. There were some other ones for which you could also get snapshots of the code, but this is the first time a NASA project actually went completely open source. From roughly 2008, more or less every year, with the exception of last year essentially, we were part of the Google Summer of Code. So I don't know if any of you know what the Google Summer of Code is, but you should find out if you don't already know. Basically, this is where open source projects gets funded by Google to recruit people to work on their open source projects. And it's amazing, basically. I mean, Google basically pay us in the vicinity of $50,000, $60,000 a year, so we get students in to work with Java Pathfinder, which is too good to be true almost. Unfortunately, we didn't make it last year because there's a selection process and we didn't get any last year. In 2009, we moved our servers away from SourceForge back to NASA because it was more flexible. SourceForge doesn't really like multiple projects very well. And now, like right now, 2015, we're in fact moving away again because NASA is now getting too restrictive with what's on their servers, and we want to be safe, so we're moving it away to Brigham Young University so that the bureaucrats can't get their grubby paws on our code. Java Pathfinder? Lots of people, but the problem is I don't know who, essentially, because it's an SVN, well actually nowadays Mercurial repository, and people just pull the code, and I have no idea basically. We don't keep track. Usually the systems don't allow us to keep track of who actually downloads it, so I have no idea who uses it. The biggest company that uses it is Fujitsu. They have spent probably 2 or 3 man-years of effort on extending it for their web services environment, and they use it very actively in Japan. It was developed in the US and then they shipped it to Japan. And since I'm on the program committee of lots of conferences, I see lots of papers coming through the process where people use JPF. So essentially from a research perspective, it's used a lot, but I have no good feeling about, there's 1,000 installations or 20,000 installations or 5. I have no idea. At NASA itself, there's a whole group, probably about 15 people, working peripherally with it. I.e., they're really doing something else but using this tool to do it. And that's a pretty active group. It was also the group in which I was until 2007. Okay, that was all the good news. Now for the bad news. The bad news is that it is an incredibly flexible system. You can do all kinds of weird and wonderful things with it, except there's no free lunch. Meaning that you cannot just use it. There is some effort involved in using it. And for the most part, the effort is involved in parts of the code that the model checker, i.e. JPF, doesn't understand how to deal with. So JPF works on Java code, so as long as it's vanilla Java code, there's no problem. But you'd be surprised to know that in all the libraries of Java, there are an awful lot of what is in Java referred to as native method calls. Meaning it's the calls to the part of the system that interacts with the environment on which that specific Java virtual machine is running. And in order to handle that, the model checker needs to understand it, basically. And in order to understand it, we need to write a little Java model that actually describes it. So another piece of Java code that describes what that thing is actually doing. And that you have to do. Every time you use Java Pathfinder in a domain where you have not used it before, you have to write these models. And you'll see now, when we get to the Android portion, this is the main work, basically. How to write Java versions of the Android environment so that we can analyze it with this tool. And of course, you also need to write suitable test drivers. Just like in testing, when you test, if you write like a silly test driver, you get a silly test, basically. I mean, it doesn't test very much. It's the same is true here. You still need to write something sensible in terms of driving the actual execution of the system. The model checker will do like all interleavings and all kinds of stuff like that, but if there's all different forms of data that the system can take as input, you need to describe this in the driver. Okay, so the key points is that it's really a research tool, but there is some production use. What the ratio is, I really don't know. It's probably 90 to 10, roughly. 10% of the use is in production systems, like in some form of industry. It's designed for extensibility, which is a really cool feature because it makes it so easy to make changes to this system. For those of you that are familiar with other model checkers, the design of this system was to be the anti-spin, or the not spin, basically. Spin is the most popular model checker in the world, by probably an order of magnitude. Except that nobody can change it, because only the guy who wrote it knows how it works. And nobody else can touch it. And we didn't want to have a system like that. We wanted to have a system that anybody can just read the code, knows what it's doing, and change it. And therefore, it was really important to be extensible. It's open source, of course, so at least you can read the source. It's ongoing, it's quite collaborative. I mean, there are a few, at STELLENBOSCH we have 3 people or so actively developing code for it, and like I said, Fujitsu and NASA, of course, and there are a few other places around the world as well where I know teams are currently working on it. It cannot find all bugs, nothing can find all bugs, right? If you don't test for the right thing, you can't necessarily find it. It's moderately sized. The core system is probably around 200,000 lines of code. It's not huge. The extensions, however, there are like so many extensions, I have no idea. I have probably 20 extensions that just I'm working on. And it's easily 20 man years of development, so it's been a while. And it's pure Java. It's in fact one of the only Java virtual machines written in Java that I'm aware of. So some people actually use it just for that, just to be able to look at the Java virtual machine's internals, since it's all written in Java. Okay, so this gives a kind of like a little bit of a lay of the land of how the system is set up. So at the very bottom you have your platform OS. This is any operating system on which a Java virtual machine runs. So anywhere where Java runs, Java Pathfinder runs. On top of that you have your host virtual machine with its native library. So the way the Java basically communicates to the platform OS, this sits at the bottom. And then you have JPF sitting here, which is part of JPF is a Java virtual machine that we have full control over. And it actually uses the library classes that is provided with Java, right? So it uses your regular Java classes. And on top of that sits whatever application you're trying to analyze. Now this application that you're trying to analyze, it also uses the library classes, right? And this is so kind of the setup. Now in terms of the internal structure of the tool, it consists of essentially two components, a search component and a virtual machine component. Virtual machine component is think Java virtual machine. It is just a Java virtual machine, but it has some funky features. For example, you can go forward and you go backwards. So forward is something that most virtual machines have, backwards is something almost no virtual machine has. So we can move the virtual machine forward one step, back one step. We can also restore an arbitrary state, which is if you go way down and you want to come way up again, you can restore some state higher. So you can imagine in order to do this, you must have very good control over the state management of your system. And that really is the core of a good model checker, is how you actually keep track of the state. Because if you kind of make it too verbose, then the whole model checking will just fail. It won't be efficient enough. Now, the important thing is that we can actually change out the bytecodes of the virtual machine. So currently Java supports, I don't know, about 220 bytecodes. We can completely take those out and put completely new bytecodes in. Like it does something completely different, for example. And I'll show you right at the end, there is an activity where we're actually doing that. Where people at NASA is actually doing that. But that's one thing you can do. You can change out the bytecodes completely. Now on the other side you have a search component. Search component, default search is depth first, but you can have heuristic searches, and you can have breakfast, A star, whatever you can imagine, you can code up here with these primitives of moving forward and backwards and so on. Now, when you have a model checker, there's one very important thing. If you have no decision points where you have to decide, am I going left or am I going right, for example, then you don't need a model checker if you don't have that, because you can just execute the program. If there's only one behavior, you just run the thing. The only thing it can possibly do is that one behavior. Now, to make model checking interesting, you need more behaviors. And we refer to that as choices. In fact, we refer to it as whenever you have a choice generator, and it tells you what all the options are. And the simplest choice you can think of is scheduling. So when you're in a certain state, in a multi-threaded program, any one of the currently enabled threads can run. And what the model checker will do is try all of the interleavings of these threads. So that's one form of choice that the model checker has. So even if it is no input choices or anything like that, it at least has concurrency-based inputs that you can choose between. You also have data choices. So for example, if you want a non-deterministic Boolean value, you can say, give me a value. It'll give you either true or false. But when you ever back up to that point again in the search, then it'll give you the other one. So basically, you get a split in your state space that way. And that's the core feature of the model checker is analyzing these different interleavings of either threads or data choices. Now, if you want to extend the system, then what you use is what's called a listener. A listener hooks into the model checking, and it listens to things that happen in the virtual machine and also in the search. And maybe most importantly, it can interact back with the system. I'll show you an example in another slide of exactly how that happens. But the point is, you can observe what's going on and you can interfere with it. So that's typically how you write an extension, because that's what you typically want to do. You want to change normal behavior of the system into something different. And here's a little example. In Java, you can put annotations on the code, and we can check these annotations. So for example, if you want to check that when you return from a method, you want to check that that return is always non-null. This is the check you want to do. Then here's what you will do. You listen on the execute instruction callback from the listeners, but meaning now you're right to the point where you're going to execute the bytecode instruction. So now you check the bytecode instruction, you check that it's a return instruction. Okay, if it's a return instruction, you check is the thing that it's trying to return null? And then, is there currently an annotation which says that it should be non-null? If those things are all there, then you know you have a violation of your property, because you were checking that returns are always non-null, and here you found a case where it's null. So now here comes the interesting bit. In order to now make the model checker find this error, what you do is you create an exception. So we have an internal method you can call to create an exception, and you make it an assertion error, and you give it a message, and this becomes a new instruction, this throwing of the exception. And then what you do is you add that instruction to the next program counter that needs to execute. So basically you create an exception, you stick it in the list of bytecodes that needs to execute, as in the next one, and then when the model checker says, okay, I'm done with this thing now, let's execute the next instruction, says, oh, I should throw an exception. Throws the exception, model checker kind of observes that as a violation and prints out the error trace. So basically this is where you have a listener, it finds out something is wrong, it pokes back into the system saying, hey, throw an exception, and then it throws the exception and you catch it. So this is like pretty elaborate, but it works well. Now I mentioned that you can swap out the bytecodes. Now one of the reasons why you might want to swap out the bytecodes, for example, is if you do symbolic execution. So symbolic execution takes symbolic values and input, not concrete values. And it basically means that certain statements that you would typically have in your code, like if you add 5 and 5, it becomes 10. While if you add x and y, and you don't know what x and y is, it becomes the expression x plus y. So there's a completely different semantics to the bytecodes if you execute symbolically. So for example, now you can swap out the bytecodes to be able to do symbolic execution. Or you can do what's on this side. In Java, you don't get overflow checking by default, right? So if you add 2 values and it overflows, it just becomes a negative value and you're none the wiser, except your program breaks. So one thing you could do in our scenario is you can override the iadd. Iadd is integer add bytecode in Java. So you can override that one to have a slightly different behavior than normal. And in this case, what you do, it might be a little hard to read here, but basically you add the 2 numbers up and you see if the result's negative. If it is negative, then you throw an exception there and say that there's an arithmetic overflow. And if you do that, then basically you now have a new set of bytecodes that can actually check for overflow. Right, so that's quite a convenient use of the bytecodes. Okay, now this gets too technical, but I just wanted to mention that one way to change the system is to create these models. Remember I mentioned in the beginning that this is the tricky bit, you have to create models. Now at least in Java Pathfinder there is a standard way of creating the models from the architecture point of view. If you have something that's native like this call to foo, you can replace it with some strange looking code here, but basically this implements method foo now inside of JPF. So whenever you have these systems where you need a different behavior, you do it in this fashion. And we refer to this bit here at the bottom as the native peer of your original class. So whatever your original one is, this is the native version of doing it. And this is one of the harder things to understand in JPF, but it's very similar to the Java native interface as we have in regular Java. So the current status is that it's very extensible, 16 years old. Lots of people use it, so please do as well. There are at least 4 people you can contact if you have any trouble. My name is at the bottom for reasons. You should contact me last. The main developer at the moment on JPF is Peter Mellets. He has been the main developer for about 10 years now. He's a very good programmer. He's also German, which means that he's very succinct in his answers to you. So when you ask a question, you might only get like 3 words back if you're lucky. But he's very good. Okay, so that's JPF. So now we're going to talk about the JPF-android extension. The first question we had to grapple with was exactly where and what code. Remember the way Android works is you take your Java code, you develop in Java, but then you essentially compile it down to something called Dalvik. Right? And Dalvik's a virtual machine, just like the Java virtual machine, except it has completely different bytecodes, and it executes on the Android devices. Okay, so now the question is, are we going to check that? Or, for example, are we going to check the source code? So we decided to check the source code. So therefore, by definition, we're targeting developers. So we are not targeting the APK files that sits on Google Play or whatever, which we download and then look at that. We don't do that. What we do is if you're developing code and your code is still in Java, then we analyze it. Okay, good reason for that is we have Java Pathfinder, so it can analyze Java code. So if we go down to the Dalvik side of things, then we have to take some, must make some decisions, right? And there is actually a current project at NASA to do exactly that. So they replace the current JPF bytecodes with Dalvik bytecodes, and they analyze it as if it's Dalvik code. You might have a question at this point, like why would NASA be interested in Android? Right? There is at least one answer, and the one answer probably is that they're actually, you might not believe this, but looking at Android in space. So basically running spacecraft and satellites and stuff on Android. And for that, they want to analyze the Android application. The other reason is NASA and Google are literally next to each other. I mean, literally, in the sense that Google is buying some of the excess space that NASA has to put up new buildings. And that closeness is not just geographically, they're also trying to work together. So this is another reason why it's a politically correct thing to do, to analyze Dalvik bytecodes. But anyway, in this project, we decided slightly differently. We're going to target developers, and we're going to look at the apps while it is still in Java. Okay? So now, if you look at an Android application, application runs in a process. So here's your application. It runs on top of the application framework, i.e. Android essentially. This in turn runs on or gets interpreted by a Dalvik virtual machine. And this whole stack here has access to some native libraries for that specific type of device that you're executing. Now the system in turn, so this is like your process, you're trying to check your application, but then there's also the system. And the system actually consists of many system services, so in some sense there are lots of little boxes in this one. And similarly, these services also run on the application framework, i.e. on Android, and it also gets interpreted by the Dalvik virtual machine, and it's also there are also libraries. In between all of this sits something called binder, and binder is the way the inter-process communication works between these different systems. Now within one Android application, you have something called an activity thread, and it has a component that's aptly named looper, because all it does is it loops around and looks at new messages in the message queue and it handles them. The messages it handles come from UI events, so if you click on your Android device, or system events, like for example, your battery is low, like the constant message I always get on my phone, like the battery is low. And then there are these you can have multiple activities that, so every activity is essentially like a screen on your application. You have services, you have broadcast receivers and so on. We're not going to talk too much about that, but these are all the components of the system that's of interest to us. Okay, so now the challenges. If you look at this thing, there is a lot of interdependencies between these different components, and all of that must be faithfully represented in the analysis, otherwise you get the wrong result. So that's quite important, but then similarly, it's event-driven. Now, event-driven seems like a small thing, but unfortunately for us, it's a big thing. Because if you analyze Java programs or Java Pathfinder, there's a main method, and everything flows from there, and it's kind of easy to handle. However, in Android, that's not the way it works. Everything is event-driven, so if you press somewhere on the screen, something happens. So we must have a mechanism to actually get in these events and see what they produce on the device itself, or on the application. So these are two of our main challenges. Now, if you look at the current landscape, what do people actually do with Android? The main thing people do is they run their applications on emulators, for example. So for monkey runner or just monkey, whatever, and you see what's going to happen to your system. That's kind of like a dynamic analysis or runtime analysis, and that gives you under approximation of what's going on, right? Because whatever you tried, that's what you see. But all the things you didn't try, you don't have any idea what's going on. Then the opposite to that end is if you do a static analysis. Now, in a static analysis, you usually over-approximate things that can happen. So you look at more things than are actually possible. Now, the problem with that is that, of course, now you get like the chance of a false positive, meaning you found some issue, but that issue is in something that can actually never happen, which is quite a problem for a static analysis. The domain in which that's most commonly used nowadays is a security-related thing. So if you want to know that if I type in my bank account number or whatever somewhere, that doesn't flow to somewhere where an SMS is sent to China, right? So you want to see that there is no information leakage. Now the third option, this is the option we're going for, is to do some form of verification. So now you want to be precise, you will be precise, up to some caveats, which I'll get to in a second. But it requires that you model certain things, and that is the caveat. Because if you model certain things and you model it wrongly, then of course your results could potentially be wrong as well. So we are sitting here at the bottom. And it's slightly closer to runtime than it is to static analysis. Okay, so now architecture JPF-android. The stuff in the dotted box here at the top in green, that's the input to the system. Out of these three, the obvious one is the actual application. Okay, so this is the Java code for the actual application. Of course, it gets compiled to bytecode, and that's what we really analyze, but essentially your app. And then the two things on the side, you can think of the inputs to the system and the oracle, i.e. what do you want to check about the system. And so this is what we take as input. I'm going to get into a lot of detail on what exactly goes to these two on the side here, so don't worry if you don't know at the moment. Now, on top of that, or below that rather, you have Android and you have Java. So the Java is all the usual Java classes you're using. Android, of course, is the usual framework that you're using. Except both of these get augmented slightly or modified slightly by having some models. Okay, I already spoke previously about what the Java models might do. For example, if there's native code, you might want to change the native code to be easier to handle for you. Something exactly the same, similar essentially happens also on the Android side, because there's also some native code and you also want to model that. So I'll get into more detail exactly what we are modeling here, but that's the thing. You want to use the Android system as is, as far as possible, but some stuff you need to model. Okay, so that you can think of as all the input. And then the system itself is the Java Pathfinder, of course, the tool we're using. All the native models that you have representative examples for here. And property listeners, which are listeners, i.e. they look at what happened, but in this case they check certain properties, and they specifically check things we call checklists here, but that's what, so these two are related. And all of this runs on your vanilla Java virtual machine, being one from Oracle or whatever. And this is roughly the flow. So you take that as input, goes into JPF-android. If you find a bug, then we translate the actions that you performed to get to this bug into the input for Monkey Runner, Dynadroid, and essentially whatever we can, but Monkey Runner is kind of our favorite. And then you can see on the emulator exactly how this error occurred. So this is kind of validation that whatever error you find is real, in a sense, or at least more likely to be real, because if you can reproduce it here on the emulator, then it's a good start. Now, what happens if whatever you put here as input actually comes through and says, no, it's fine, we couldn't find a bug? Okay, what you do then is that the idea in the beginning is when you drive the system here, the inputs to the system might just be a subset of the possible inputs to the system. So you're not giving it all the possible inputs, you're just giving it some inputs. Like for instance, there might be 5 buttons you could click on, but for this thing you only click on the first one, for example. And then what we have is another component, and this is kind of ongoing work, so it's not done yet, but we can dynamically look at the possible behaviors from the user interface side of the system and automatically generate all possible behaviors up to a certain bound. So for example, all behaviors up to 5 actions deep or something like that. So that gives you a much more elaborate input to drive the system work. And in that kind of, in some sense, it cycles back here and runs again. So at the first pass, or first 2 passes maybe, you just create your own input scripts here, stuff you want to change. And then later on you develop more automatic ways of actually coming up with all the possibilities of what can happen. Okay, so the work consists of essentially 3 main components. We are first going to look at environment modeling. So basically, what did we need to model in order for JPF-android to run at all, basically. And then we're going to look at what goes into the input scripts and what goes into the checklists. So in terms of the environment model, model checking only really works if you have what's called a closed system. A closed system is one in which the analysis engine has full control over everything that can possibly happen. Okay, and what that basically means is you cannot communicate with something over a network or something like that, because there's no way the model checker can have complete control over that. So what happens is you have to model certain portions. And first thing we do is remove unwanted code or unused code. Now, one of the main things that we never use is the Dalvik virtual machine, because we're not actually executing code on the Dalvik virtual machine, so we can rip that out completely. So all the code that has to do with Dalvik virtual machine is just gone. We're not interested in that. And the other thing we're not interested in is any visual aspect of the UI. So if you're going to put up a purple box, we couldn't care. For us, it's just a box. And all we want to know, if it's a button, did you press the button or not? That's important. What color the button is irrelevant to us. So we never check any of that. So all the code that's related to that just goes away. So that's some of the stuff we rip out. And then, of course, all the stuff that's involved with native calls. Since we can't handle native calls, we have to create models for the native stuff. Now, that would have been very simple. If the whole rule is you cut out things you're not interested in, and you cut out things that are which you cannot handle, like native methods, that would have been a perfect world. Unfortunately, it goes a little beyond that, because we also simplify certain things that just has some bloat in it, essentially, that we're not interested in. And unfortunately, that's a little hard to define exactly what that is, because that's something to do by hand, and you cut certain things out. A kind of a good example of something like this is if you have just a normal Java, if you have container classes, like a linked list or a red flag tree or anything like that, then every time you do something to that, say red flag tree, if you add something, there's actually a little counter that says you've modified it +1, right? So this is the 17th modification to this structure. If you modify it again, it's 18, and then 19, and so forth. Now, one of the things you do in model checking is you take the whole system, state, and you match it to previous states to see, have you seen the state before? Because if you've seen it before, you don't want to analyze it again. That's the whole reason why model checking is efficient. Now, unfortunately, if you have a counter that keeps on incrementing every time you touch something, you will never find 2 states that match, because they're always different just with this counter. So that's the kind of thing that we cut out. Right? Because we know we don't want a counter like that, because we know what that's going to mean for us in the end. So that's like model checking folklore, and in order to create these models, you need to know a bit about that, because otherwise the models they're just not going to work. So you have to do stuff like that. So there's some simplification going on when you create these models, and a little hard to define exactly what that is. It's more like sucking a thumb and kind of. Okay, so what do we need to model? We need to model the component lifecycle management. So has the app started? Has the app been created? Has it started? Is it suspended? All that kind of stuff we need to track, because if we don't know in what state it is, then you cannot do the right actions on it. We need to know what the GUI looks like. So in Android, there's this notion of inflation of the GUI, so like you blow it up into what it's supposed to be. We need to track all of that precisely. How the GUI is represented to some degree, not like what color it is, but what actions follow what other actions. So if you click on a certain button, does that start up a new activity? You need to know that. Otherwise you can't handle things correctly. You need communication with system services. So for example, if the battery is low, you need to know what to do with actions like that. And in native services, meaning these are things that you want to be able to handle in your applications, but stuff that the model checker fundamentally cannot do. For example, communicate via a file. If you write something to a file, a model checker cannot create a file on the file system as you're analyzing something. Because what will happen is you'll just have a bazillion files on your file system when you're done model checking. You cannot have that. So you have to model how a file operation works and so forth. Okay, so the component lifecycle, I'll skip over this. This is just the regular stuff on how threads are started and so forth. But this must be tracked. In the user interface, you must know that which groups is above which other groups and what views are visible and so forth. And in terms of precisely what you need to know about the views, you need to know what is currently visible. Because if it's not visible, nothing can interact with it at this point. If it is visible, it must be enabled. Containment, like in which activity or which button on the activity links to which other button on the activity, that's also important. And then of course which listeners are actually active at that point, which ones are registered to listen to certain buttons being pressed. Now in the system services that we handle, the grayed out ones are ones that we currently don't support in our system. Right? So the activity manager, battery manager is there, connectivity manager, package manager, no account manager, no audio. We do support the camera because one of our applications we were checking required camera, so therefore we do support this service. And some more that we don't currently support. Some of the native services that we actually do support as well is we can handle databases, network communication, threads, resources, the GUI inflation, which I already spoke about, input processing and message processing. Those are all things that we can actually handle within the applications. Okay, now, when we started off, we decided that we didn't want, right from the beginning, a system that can just do everything, so to speak. In model checking terminology, we refer to this as the global environment or the universal environment. It's something that can just do every possible action at every possible time. That's like monkey in Android. Like, you know, you can just go like this and press anything, or whatever you accidentally press on, that's going to happen. We didn't want that. We wanted a more focused, let's call it script, that we could execute. And in the script, what do we want to have control over? We want to have control over the user events, so everything that you can typically do in the application. But we also want to control over the system events, because we wanted the capability to allow you to actually analyze the different things that will happen if the battery is low and when the Wi-Fi is going down and so forth. And so here are a fairly comprehensive list of all the user inputs that we support. So button clicks are supported, you can edit, you can set text to certain things, you can select them from a list, check boxes, radio groups. We also support device action, so for instance, you can rotate the device and so on. There's an awful lot of bugs in Android comes from the fact that you were like this on your app and then you turn the phone around, and the moment you do that, your app just froze or crashes or whatever. This is something we wanted to check. And there's a whole bunch of things we still don't handle that. In terms of system inputs, for example, we can say that the Wi-Fi is on. We can do things with the battery. We can say it's 20% or 10% or 100% or whatever. And these are very useful things to do because it's now quite easy for us to check what are you app going to do if your battery gets low. We just, in our input script, we just say, do blah, 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 now make the battery really low and now see what happens. So it's, that's quite convenient. Okay, so this is what the inputs actually look like. So there's a notion of a section that's really for readability, but the sections correspond to activity. So whatever you can do in a specific activity, that's what's described in one section. The any means that this is a non-deterministic choice. So you can do any of these three things. so non-deterministically. You can either do like button 0 click, button 1 click, or these three things in order. You have repetition, so you can here say I want to repeat something twice or something like that, but you also have like infinite repetition, so repeat star, meaning you're going to just keep on doing this. Why can you do that? Because in model checking you can match the state. So if you have seen the state before, this thing will actually get terminated, even though it looks here like it will infinitely continue. Here's an example of a specific one we have, which is the RSS reader. It has a bunch of non-deterministic things you can do here. So you can set the Wi-Fi to on, you can set the battery full, and then you can do this repeat thing here at the bottom, where you can set the battery low and stuff. So you can do all kinds of things to set up your system before analyzing. And the last component we're going to look at is what can you check with these things. So we came up with this idea of a checklist. Okay, a checklist, you'll see an example in a second, but it verifies a trace against the behavioral specification. And the behavioral specification is in this checklist. So whatever is actually happening, you're checking it against this. Now, interesting question is, what is a checklist? Well, a checklist, if you compare it to a regular expression or LTL, it's fundamentally different from LTL because LTL matches infinite sequences, or infinite words essentially. This is always finite, so it's different from that. And it's a subset of regular expressions. So there are certain things in regular expressions you can specify which we cannot specify. It can handle asynchronous apps. Well, all apps tend to be asynchronous because you can check for any event that happens. It can also handle multi-threading. And multi-threading can be kind of tricky because what happens here is that something might happen in the main thread, then an asynchronous thread gets spawned, and it does a bunch of things. And then it comes back to the main thread with some message, and you want to check something happening in the main thread, something happening in the asynchronous thread, and then maybe something back in the main thread. And you have to therefore specify which threads does stuff. For example, if you have a bunch of asynchronous threads, you might want them all to do something, or just a subset to do something. And these are all supported within this system. So here's an example. So the general form of a checklist is something like this. So there's a name, there's a guard, and if the guard's satisfied, you check basically the checklist. So here we have update success. This is the name of our checklist. If you do an update, to initiate an update, I press the button that will do an update. And the Wi-Fi is currently not down, so not Wi-Fi down, and the battery is not low, then you should actually run the update, and the update should display when you're finished. So that's a checklist. And how do we know where we are in this checklist? We specify annotations in the code. So for example, the run update is whenever this method gets called, that's where run update is. And we want this only if it's in the update thread. And here, for example, this one is only if it's in the main thread, and similarly this one. So now if we look at a graphical representation, we want update here in the main thread. Then we want the run update here in the update thread. At this point here, right when it makes the switch to do the run update, you want to know that the Wi-Fi is currently on and the battery is not low. These are checks that are done with a call, basically, to the system. So they're instantaneous. This may be something that's a little confusing. And then the update display should happen back in the main thread because that's where the graphical part is. So semantically, it looks a little like this regular expression. What is important is that it can only kind of not be checked if one of the Wi-Fi or the battery low things are happening only in this state. Because there's a certain point in time where you check these things. And that's when it needs to be on. So the Wi-Fi must be on when you check it, and the battery must be not low when you check it. It can actually, if you switch off the Wi-Fi after this, then your checklist will fail, but it's not because the precondition failed, it's because something happened later on that switched off the Wi-Fi. So these are the kind of things we're checking. And I guess it's simple to argue that this is a lot easier to understand than this monstrosity at the bottom here. So this is the whole point. It's something succinct that you can write to check your problem. Okay, so in conclusion, the current status is we're right now everything's kind of working, but we're making some small tweaks to the system. So it's not It's not quite available yet. We're also running a lot more examples because we have a bunch of examples, but not constantly in Android. There are more benchmarks coming along and stuff. And what we're currently doing is just running more and more of these to see where we are at. And roughly about 3 months it should be ready that everybody can use it. On the next slide I'll give you the URL that you can already go to download everything, but right now I wouldn't say it's perfect to run. One of the things that happened over the summer last year, that's the Northern Hemisphere summer, is we actually tried to see if there wasn't a way that we could be more rigorous with the creation of these models, because like I said, it's a bit of a thumbsuck as to what exactly goes in a model. And that's not quite good for a PhD. It's better to be more systematic about it. So we tried to be more systematic. So we tried to use 2 tools for Java. One that allows you to slice things, and another one that can analyze the side effects of certain changes. And really what we found is that if you want to use slicing for generic code across all apps, slicing doesn't really work. Meaning that you don't slice anything away. Everything essentially still stays there. So a slice program is roughly the same as the original program if you're too generic about it. Now there's another group that we've been working with now that has a very similar tool to this one. They slice per app for a specific property, and in their case specifically security. And if you do that, then you can actually slice some stuff away. So a very focused slice works, whereas a generic one doesn't work. So for us it can work, but for them it's working. And we use the side effect analysis tool, and the way you use that is you say, well, if I change this thing here, what else gets influenced by that? And what we managed to do there is that actually helps you to create the models, but manually. So because if you make a change here, then it tells you should keep this and keep this and keep this because it has certain effects on this change, or there is certain effects on this change. And therefore keep those parts of the model. But it's not an automated process to come up with the models, it just guides you to create the model. So that's been useful, but not as useful as we probably would want to do. And as I already mentioned, we do this dynamic input generation at the moment, where you take the app and you dynamically discover all the things that you could potentially do with this app. And that's almost done, essentially, so it's pretty close. And then lastly, which is the next step, is symbolic execution, because it's one thing to know what you can do on the app, but what if you need to add some text somewhere? How do you know what text you should be adding? So if you do symbolic execution, it'll tell you, like if you want to access this part of the code, then this string needs to be foo-bar. If it's foo-bar, then you'll get there. If it's foo-foo, you won't get there. So that's what a symbolic execution engine can tell you. So that would be the next step to enhance our environment generation. And I believe that's it.
Move to the second part of the presentation. Questions from the audience. I don't have a Wi-Fi microphone here, but we can speak a little bit loud.
When you do the checklist, do you analyze all the paths that could like fail something if it doesn't have Wi-Fi or sufficient battery?
So the checklists are the checklists go with a specific input script. So just for that input script, you are checking the checklist. However, in the near future, we will be able to do the step here, which we generate dynamically all the possibilities, say up to a certain number of actions on the UI, in which case it will then check it more exhaustively. But the system right now, you specify potentially non-deterministic input, i.e. you can press this or that or whatever, but it's still a relatively fixed input, and for that we check the checklist.
But even so, you still have some non-determinism.
Yeah.
I have another question. For me, it's got a little bit confused the difference between the listeners and the model, because you have exceptions thrown in both models. But if you already have the exceptions, why do you need the model? I mean, the checklist to check all of them, how they are connected? Because it's from the exceptions that you are going to check the checklist.
Yeah, actually, okay. So sorry, I was obviously a bit unclear there, because the exceptions really has nothing to do with checklists. Right? that little example I showed with the listener and the checklist, that's like a special example. That's something that you rarely do in reality. The way it usually works is you write a special kind of listener, which we call a property listener. And the property listener checks whether certain properties get violated. And for example, for the checklist, what it'll do is it'll keep track of essentially this automata here. And every time an action happens that can make a change to this automata, it'll make the appropriate change. And when the sequence is done, for example, if you're not in an accepting state, then you will say, okay, here's an error, because it didn't end up in an accepting state.
Okay. Just another question. You said that you just checked the Java code. Is there any kind of error that you cannot detect in the Java code, but it appears in bytecode?
That's a very good question. I don't know. I would hope not, but I cannot absolutely say that. I mean, there is a chance, I guess.
This might be a little off topic, but what kind of knowledge do someone need to work at NASA, and how would you proceed to do that?
Obviously not a lot of knowledge, because I don't know. Actually, it's dead easy. It's really not hard. But the way it always worked for us, we had tons of students come through from NASA. I'm assuming you're asking in the context of being a student, what you mean. So, if you are doing anything that essentially overlaps with what those researchers are doing, and Lucas would be able to tell you whether you're doing something that overlaps with some people at NASA, then you literally send them an email and you say, hello, I'm Johnny, and I do this stuff, you might be interested, do you want to take me as an intern? And you'd be surprised how often the answer is yes. And then you can go spend a couple of months over the summer or whatever you can spend there. This happens all the time. So you really don't need any special knowledge, but there must be some overlap between what you want to do and what they want you to do. But you can initiate it. That's not a problem.
Some more questions? Yeah, I have one question. Can you tell how large are the birds that have already verified JPF and also JPF-android? It's still a prototype, right?
Yeah.
So I'm going to check out but for JPF, it's going to be
Yeah, so
to check some of those programs and how large they are.
okay, so I can tell you what the claimed largest program is that I know of, which is Fujitsu, claims that they have a program that is just over 100,000 lines of code. However, I would assume it might be 100,000 lines of code, but I assume the number of lines of code that actually got analyzed specifically probably is in the order of 10 to 20,000, because that's been my experience. Like around 10 to 20,000 lines of code, you can do something with it. But if it becomes if it gets up to 50, 100,000, then realistically, the poor model checker. Remember, it's after all a virtual machine as well. A virtual machine that runs about 1,000 times slower than the real virtual machine, right? So you can imagine anything that's significantly large, requires a lot of computation, will be significantly slower in this environment than it would typically. With Android, this stuff has been small. This is like a few hundred lines, a few thousand lines, small things. Nothing significant yet.
So, and how long does it take for to check that large HTTP application?
Well, it's usually quick because you'll find a bug. And when you find a bug, you stop. So typically, I mean, I personally, if a model checker runs for more than about 10 minutes, I stop. Because if it's not finding a bug in 10 minutes, I did something wrong. Because usually there is a bug to be found. It's just that I might have written the wrong environment, i.e. driver. So the bug is if you press A, then B, then C, my driver only allows you to press A and B. And it never finds the bug because it never presses C. It's that kind of thing.
Some more questions? So let's thank again
você.
Bem? O que estava assistindo de novo no Netflix? Chegou atualmente?
Não vi ainda não. Cara, eu